So today's lesson is on dynamics and laws of motion. Today's lesson is dynamics and laws. My name is Ishiki, like I said. So let's see what we'll be learning for today. We'll be learning the Newton laws of motion. We'll also understand the concepts of different types of friction. We'll also be analyzing equilibrium of forces and solving some problems involving inclined planes. So these are our objectives for today. At least by the end of this class, I'm expecting that most of us should, that all of us should be able to explain the laws of motion. I think positive states the Newton's laws. There are three of them, and we should be able to state all of them. And also, we should be able to different types of friction, be able to define friction and different types of friction that come out in our exams, in JUPEB exams. So let's head into the lesson for today. So in today's let's start with the introduction.
Yes.
I don't know if you can see my slide. Okay. Introduction to dynamics. So dynamics is, we've heard of statics or kinematics. In one of our classes, I think we talked about kinematics, and in kinematics is like opposite of is the general word for all the motion in physics. It's the general word for all the motion in physics. So these kinematics can be divided into dynamics and statics. So this dynamics is actually the portion of motion that involves movement of an object as a result of applied force. So I have here that I define it as a dynamics is the branch of physics. I didn't really write the branch of physics though, but it's the branch of physics or the branch of kinematics that studies motion of objects or that deals with motions of objects and the forces causing this motion. So there is this saying that people say, or that we've been hearing. I don't know how many of us might think that it's actually one of the laws of finding out. So they said for every action, there is always an equal and opposite reaction. So this is actually a truth. It's actually a truth. They say a body, something that is not moving, you cannot just stay. Maybe you drop a stone on a table and all of a sudden the stone will just start moving, except it's being acted upon by an external force. Except something else, either wind tries to change its position, or maybe there's an earthquake and it's kind of sending waves that is causing the movement of this body. So bodies will not just stay and start moving, except there is something that is propelling them to act. Even human being body, if we don't have our internal energy that helps us to move, we don't even have strength, we will not have energy. And once we don't have energy, there will be no force that we can expend to our bodies to make it move. So every object that happens to undergo motion is always as a result of an external force, sometimes internal forces, but majorly from external forces. So let's go on. The central to dynamics are the Newton's laws of motion. So when you talk about that dynamics, you are talking basically of the Newton's laws of motion. They are like the building block for dynamics. Dynamics is a portion of physics that deals with motion of objects and also the study of forces that cause motion. So I'm just reiterating this so I will be able to have an overview of what this thing is. So let me just say it one more time. When you hear the word dynamics, it's talking about that portion of physics that deals with motion of objects and also the forces that causes this motion. I just hope we can be able to pick two portions of this definition, or would I say the three key points of this definition. A dynamic portion is a branch of physics, deals with the study of motion of objects and also the forces that causes this motion. So it deals with the study of this motion and also the forces that causes this motion. and it's a branch of physics. It's just a cut out of physics and deals with the study of motion. I'm reiterating this thing so it will not be something that will start that maybe you happen to miss during this course of this, because that's the major topic for this week's lesson. So it's that branch of physics that involves the study of objects in motion and the forces that cause this motion. So let's move on to our next slide and see what we have. As I said before, I said that this dynamics, it's basically dealing with the laws of Newton's laws of motion. It's basically dealing with the Newton's laws of motion. So, and these Newton's law of motion, there are three Newton laws of motion. And we have the first law, the second law, and also the third law. So we have the first law, second law, and the third law. So we have here for the first law, we're dealing with the first law first. It's also known as the law of inertia. The Newton's first law is also known as the law of inertia. So this law, it states that an object will remain constant or remain at rest or uniform motion in a straight line unless acted upon by external forces. So this is what I was trying to mention. This is the law of inertia. And it states that any body at all, any object will continue in its current state of motion, whether it is in a static state of motion or it's in a moving state or that's dynamic state. It would remain in that state at a constant movement. If it is in motion, it will maintain that constant motion. If it is static, it will remain that static position except there's an external force that is acted upon, that acts upon that body. So let me bring it to our understanding. We might not be able to relate this thing because usually there are forces around us. These are Earth. But where you would be able to see this thing happen is when you go to space. I don't know, many of us would have seen movies or even movies or what they call them, movies basically, all these sci-fi movies where they go to the space and they found things just floating around in space. Even our Earth, they say our Earth is always moving around the sun. Have you asked why has the Earth not stopped moving? Why has it not stopped moving? The major, or I say the most defining reason is because the space, our space outside our Earth space, it is actually void of any form of most forms of motion, of force. It is void of most forms of forces. So what do I mean? Unlike inside the Earth, we have winds blowing around, we have gravity acting upon bodies, we have several forces, electromagnetic forces acting on objects inside the Earth. Outside the Earth, we just have some forces, but these forces are, let's say, I can say they are light comparing to the ones that are inside the Earth. The gravity inside the Earth is very severe compared to when you go to space. Things outside the space, they will continuously float in the air. And that's if you just drop a piece of stone on the air in space, it will continuously keep dropping in space or keep floating in a particular direction. If you touch it, it keep on moving in a particular direction continuously. I don't know. Someone said, I don't know if someone is raising up their hand. If you are sorry, before I continue,
Yes, sir.
if you have a question or you have something to tell me, please just open your mic and say it so that at least I would be able to, my attention will be drawn to you because I can't really hear you guys. So I would like, I can't really see your messages most of the time. So it would be best to just say something. Just turn on your mic and say something. Just excuse me, sir, or something like that, that I'll know that you're talking. Someone's hand
Yes, sir. I wanted to
is
complain
raised up.
about the screen. Yes, sir. I wanted to complain about the screen. I could not see the screen, but now I can see it.
Okay. Thank you. So, let me see. Oh, I think okay, let's just go on. So you can see my screen, right?
Yes, sir.
No, sir. I cannot really. Okay, I've seen it. I'm seeing it.
Okay. So let's continue. As I was saying, our Earth, in space, it continuously moves around, continuously moves. I think I just think I'll need to do something on this call. I'll need to stop sharing my screen and share it again because it seems like I might not be able to hear you guys well. Let me just end the call, rejoin this call, then we'll start sharing again. Let's continue. Just pardon me. Okay, so let me share my screen again. I think I should be able to hear you guys well now. Can someone please just say something so I could hear you guys at least?
Yes. Okay,
Okay,
I'm
thank you,
talking
thank you,
now.
thank you.
Can you hear me?
Yes, I can hear you. So let me go back to the slide I was at before I ended this call. So this was where we were at, and I was trying to explain that the Earth is continuously moving around the sun. It has not stopped. Every other planet, they are also moving around the sun. They've not stopped. This is because of the lack of force or the lack of significant force outside space that could reduce its motion. So that this first law of motion that states that an object will remain constant at rest or in constant motion unless it's been acted upon by an external force is very true. It's very true. As I was giving an analogy at the beginning, I said a stone would not just jump up from the table, except something hits or something distorts its position. Something has to affect it from staying at its constant state. And if you throw something, when you throw something on the air, as mean we are in space, if you throw something on the air, it's continuously be moving at that speed continuously, forever and ever and ever and ever. Continuously be moving with that speed forever. But now, if it were to be inside the earth, it's forces that thing that make objects drop is because of forces like gravity. So gravity, as you throw something, as it is moving in the air, gravity and even wind speed would reduce its speed before the speed would turn to zero and before the body would start dropping. When we are teaching projectile, this is actually what usually happens. We said that when the thing gets to a maximum height, then the velocity becomes zero and it starts dropping again at speed of gravity, at the acceleration of gravity, as an acceleration due to gravity. Sorry. So this law of inertia, it's one very true law. It's a very true law. So the important thing to take away from this is you should be able to know this law, that this is the first law of Newton, and it states that an object will remain at rest or in constant motion, except it is being acted upon by an external force. So there are two things when you're trying to state this law. If you are considering a body at rest and also a body in motion. So for the body at rest to remain at rest forever, for a body in motion, it will remain at that same motion forever, except it is being acted upon by an external force. So this is the definition of this Newton's first law, and it's also called the Newton's law of inertia. So here it said the law introduces the concept of inertia, which is the tendency of an object to resist change in their motion. The greater an object's mass, the greater its inertia in real life. Friction or air resistance will usually act as an external force to alter motion. So this is what I was saying. Our Earth is very big. So now, any force that is existing, there are few forces in the space. Any force that's existing is very small compared to the size of the Earth. So that's the reason why before the Earth can stop in its movement around the sun forever as it's moving, the force that needs to act upon it needs to be greater than the motion that the Earth is moving at. So let's try to leave that aside first and focus on the other portion so we can move forward. So the key idea for this law of inertia is motion does not change unless something causes it or something, and that something has to be a force. I don't know. This is what the so this is like the summary of the whole law of inertia. That everything would not change in their state of motion except something else acts on it, and that something else is usually a force. So let's go to our next slide and see what we have there. So this next slide is talking about the coefficient of static friction. So this coefficient of static friction, it is a unitless value that represents the maximum resistance between two surfaces before motion starts. So when we're talking about this, in our first slide, we said something about a body being at rest and it would not. We mentioned something about inertia, and we said that the inertia of a body is like the opposition to motion that the body gives. It's like the strong head that every body, like every object, always have. That's what inertia is like. It's like that strong head that they'll say they don't want to go, they don't want to go. So this strong head is related to a constant that's called the coefficient of static friction. So before an object would move, this particular strong head needs to be overcome. Like before you can be able to make a stone leave its position, you must be able to have enough energy that it surpasses this strong head. It's just like a stubborn child. If you know stubborn past that child, sometimes you might not be able to force that child to do a particular action. You have to have stronger, I don't know what I would call it, stronger will, or you have to have a stronger energy than that child for you to be able to make that child move. The same thing applies when you're trying to pull a goat. If you don't have strength, the goat would be standing at one spot, trying not to move. It will be exerting its inertia on its position. And for you to be able to cause that goat to move, your energy needs to be greater than, it needs to overcome that goat's inertia. That is the goat's resistance to motion. So this inertia could be in form of friction, it could be in form of weight, and it could be in different form. But now inertia as a whole, it is that resistance that the body is trying to give to motion. It's not necessarily friction. It is just the general name for every form of resistance that every body gives to resist motion. So, and there is a constant that is related to this inertia, and that constant is called the coefficient of static friction. If you don't overcome this coefficient of static friction, you can never make any object move. Even your hand, there is always a coefficient of static friction. If you keep your hand on a table, except you have strength to lift your hand will not move. This kind of thing will happen when someone is very, very hungry and the person has not eaten for probably 7 days and the person is very weak. You don't have the force to be able to lift your hand. Your hand that you have been moving on a normal, like as if it's nothing. At that state, it might be difficult to lift your hand because your energy now, you don't have the force to be able to overcome the coefficient of static friction. I don't know whether I'm communicating at all. So this is the maximum energy that needs to be overcome, the energy that needs to be overcome for an object to start moving. Without a coefficient of static friction mean, and it's usually represented by this constant, by this Greek letter mu. It's represented by this Greek letter mu. Let me use my illustrator now. So this letter mu here is used to represent the coefficient of static friction. So it is it has a formula that they use to express this coefficient of static friction. The formula is that F equals mu n. So mu is like u, and this is the formula. It's usually the formula that is relating to the first law of motion, Newton's first law of motion. F is equal to mu n, where F is representing the force, n is representing the normal, then mu is representing the coefficient of static friction. Where this normal now, what normal means is it is the perpendicular force that is acting on any body, any object at all. The perpendicular force, usually the perpendicular force that's acting on an object compared to where it is standing on. So let's move on to the next slide. From this next slide, we will see how this formula can be applied in questions, or how questions under this topic usually apply. So now this is our question 1. Our question 1 states that a block of mass 5 kg is placed on an horizontal surface. If the coefficient of static friction is 0.4, calculate the minimum force required to just move the block. So this question, they're trying to ask you, if an object has a mass and we want this object to move. We want this object to move. The object is on a horizontal plane and we want this object to move. So then before I draw this thing, before I explain this stuff, let me draw to explain what this normal actually means. Assuming we have this plane here and we have our objects on this plane, there is always going to be a force. There's always going to be a force that is perpendicular to the place where this object is staying on. There's always going to be a force that's perpendicular to the plane where this object is lying on. So that force, that is, what I mean by perpendicular is that it means that it's at 90 degrees to the plane. That the force is at 90 degrees to the plane where this object is lying on. So that force is what they call the normal force. And the normal force, when the object is staying on an horizontal ground, like on a flat surface, on an horizontal ground, let me use horizontal ground because that's the real expression. When it is on an horizontal ground, the normal is equal to the weight of that object. So if you're writing down, I would like you to write these things down. I'm trying to explain what normal force means, what the normal means. Because I said the formula is F is equal to mu, that is UN. That's the formula I said is the formula to get, or the formula from Newton's first law. So this formula, the N in that formula, I said it is called normal. So now this normal now, it is the force that is acting at 90 degrees to wherever the surface that any object is placed upon. So if an object is placed on a slanted surface, that object, the normal of that object will also be, the surface like this is horizontal. So the normal would also be perpendicular at 90 degrees to that, object. So that means to be like this. The normal will be at 90 degrees to that object. I don't know if you are seeing what I'm showing. So the normal is going to be at 90 degrees to that object. It's always be at 90 degrees to that object. So the normal can be in different directions. It can be in different directions, but the main way you determine the normal of any object is that the place where the object is standing on top, draw a vertical or a line that is perpendicular to that plane where the object is lying on top. That line is called the normal. So in the case of horizontal objects on horizontal surface, the normal is always equal to the weight. The normal is always equal to the weight. Normal is always equal to weight. So as I was saying that if you write down, I said if you're writing, write that on a vertical plane, the normal of every object on a vertical plane, on a horizontal plane is equal to the normal. Is equal to the weight. I don't know why I'm mixing words, but what I'm saying is that the normal for every object on an horizontal plane is equal to the weight. That is, N is always equal to W when the object is standing on an horizontal surface. N is always equal to W when the object is standing on an horizontal surface. N is always equal to W when the object is standing on an horizontal surface. So I'm repeating this thing because it's important that I repeat it. So let's see how we solve this question. So question 1 says, a block of mass 5 kg is placed on a horizontal surface. If the coefficient of static friction is 0.4, calculate the minimum force required to just move the block. Calculate the minimum force required to just move the block. So now, this formula we are going to use because we are looking for the minimum force, and they give us the coefficient of friction, of static friction. So this formula we are using is the formula from the Newton's first law. That's F is equal to coefficient times N, that is UN. So now they gave us the coefficient as U from the question. They gave us our U as 0.4. And they from the question, if you don't know, if you did not hear what I said in the previous time, you will not know what the N is. But they actually gave us our N. N in this case, because they said they're just standing on a horizontal surface, N is the same thing as the weight of the object. And the weight of the object is always equals to the mass of the object times acceleration due to gravity. Weight of every object is always equal to the mass of that object times acceleration due to gravity. I'm repeating myself again. The weight of every object is always equal to the mass of that object times acceleration due to gravity. So that's W is always equal to mg. So now, since this in this case now, our N is equal to our W. So now our N can be said to be equal to mg, meaning the mass that they gave us on the question, the mass, 5 kilograms, times the acceleration due to gravity, which could be 10 or 9.8. But for this one, I'm using 9.8. So when you multiply it, you get your N value to be 49 Newton. Then you then use your formula from your Newton's first law, which states that F is equal to UN. So our U they gave us on the question as 0.4 times 49, which we've gotten as our N. So our final answer would then be 19.6. I don't know if anybody is confused. If you are confused, I would like you to just draw my attention to the point where you are confused so we could resolve it. Are you guys hearing me?
Yes, I'm hearing you.
Yes, sir.
It's okay
Yes, sir.
for me.
So I can't see the screen.
Okay. So you can't see the screen.
Yes, sir.
Can every
Okay, I'm
person see
seeing
my
it now,
screen?
sir. I'm seeing it now, sir.
Okay.
Yes, sir.
Okay. So as I was saying, this is the solving for this kind of question. So you could see this kind of question in your exams. You could see questions where they will tell you, they could give you the coefficient of static friction, or they might even give you the force and the mass of the object. And they will tell you the object is on an horizontal plane. So the things you would always look for is where is the object standing on top or upon? What type of surface is the object standing upon? Is it an horizontal surface? So once you've heard that it's an horizontal surface, the next thing you would know is the normal is equal to the weight and is equal to mass times acceleration due to gravity. That is m times g. Because m times g, and m is the mass, g is gravity. That's acceleration due to gravity, and that's gravity can be 10 or 9.8. So once you can be able to decipher all these parameters, you should be able to get your final answer. It's actually a simple type of question, but if you don't really know where to start, you might not know what to do. So the ways to identify the question that you're using this kind of stuff is when they mention something about coefficient of static friction, your mind should always tell you first or draw you back to Newton's first law. Once you see in a question that they're mentioning coefficient of static friction, your mind should always draw, probably I might be able to use the Newton's first law. And this is what the Newton's first law states. F is equal to UN. I hope it's clear.
Yes, sir.
Yes, sir.
Let's go to the next slide.
Yes, sir.
Yeah, someone called me. So let's see, these are question 2. The question 2 states that a 10-kilogram box remains stationary on a rough horizontal floor. Explain why it doesn't move and calculate the maximum frictional force keeping it at rest if U, that is this our mu, is equal to 0.3. So as I said, once you start seeing them mention this mu, your mind should take you automatically to the Newton's first law's formula, that F is equal to mu n. Think of its possible iterations that could give you that answer. Think of its possible iteration that could give you that answer. So now, once you've thought of it now, you can now start thinking of solving. So for this question, now they gave us that the force, they said we should find the frictional force. So frictional force is similar, is a kind of force. So then they're asking you to calculate the maximum frictional force. And I said the formula, that F, the formula of F equal to mu N, that F is the force, the necessary force required to force the object to move. So the same way, that force can be likened to friction, because before you can make an object move, you should be able to overcome friction. Before you can be able to cause an object to move, you should be able to overcome friction. So this question is just almost the same with the first question. It's just that in this case, they kind of twisted the question in a way that you could be confused. But as I told you, one of the hacks to actually figure out this kind of question and when to use this formula, you would see them mention stuff about coefficients of static friction, or they will tell you mu is equal to a particular value. Then once you've seen mu, either they're asking you to look for mu or they gave you mu in the question. So long as they're seeing mu in the question, just your mind should go to the first law. And once your mind goes to the first law, the next thing you should be looking at is where is the object standing upon? Is it an horizontal plane or something like that? Because if it's not horizontal, it's usually going to be an inclined plane, but we are not dealing with inclined plane for now. Later on, we would find how we deal with inclined plane. So for this kind of plane, when you have horizontal plane, usually you see questions on under horizontal plane. When you see that the object is standing on an horizontal plane, the next thing you will do is your mind should take you immediately to the Newton's first law formula that we just gave now. The F is equal to UN. Then look for how you can find the parameters. Since it's horizontal, we already know that our N is equal to W, and the W is also equal to M times G, that is mass times acceleration due to gravity. So they gave us the mass of the body as 10 kilograms, sorry. So you multiply 10 by 9.8. Once you've gotten it, you can then multiply it by the coefficient of static friction, and you get your final answer. As we can see here, the answer is 29.4. I don't know if anybody here is confused about the solvings we can see on the screen. If you are confused, just tell me so that I can possibly verify you on where you probably have been lost. Is it clear?
Yes, sir, it's clear. It's clear
Yes, sir.
for me.
Okay. So the key takeaway from this portion is always observe the question. Did they mention anything about coefficient of static friction? Once you hear them mention something about that, the next thing you should look for is where is it standing upon? Once you found, okay, it's on a horizontal plane, or no, it's on an inclined plane. If it's on an inclined plane, they'll mention the angle or something like that, but we're not dealing with that for now. Or we're focusing on horizontal plane. So this should be a bonus question. Anytime we see coefficient of static friction and we see horizontal plane, it should be a bonus question. You should not think it twice. Our head is just spin straight up to Newton's first law of motion. F is equal to UN, and look for how you could get the parameters and look for what they're asking you to. So the formula you should always use is always this formula. F is equal to UN. So let's move on to the next slide. So on to the next slide. The next slide is talking about Newton's second law. Newton's second law. So as we have the Newton's first law, I said these laws, Newton's laws of motion, are the laws that dynamics is based off from. So this Newton's law, they are the central or the core of dynamics. When you talk about dynamics, Newton's law should always come to your mind. When you talk about dynamics, Newton's law should always come to your mind. The laws of Newton should always come to your mind. So for this case of Newton's law, we are now at the second law of motion, Newton's second law of motion. And this second law of motion states that the acceleration of an object is directly proportional to the force applied to the object and inversely proportional to its mass. So the law states that the acceleration, so they mentioned three major parameters, that acceleration is directly proportional to force and inversely proportional to mass. So this is the summary of the formula of the law. Acceleration of any object is directly proportional. Did someone call my attention?
Sir,
Okay, I'm listening.
sorry. You said the acceleration of an object is directly proportional to the force applied and inversely proportional to the
Yes,
mass. But looking at it,
yes,
it looks like the mass is directly proportional to the force, so as the acceleration too.
yes. So see how you'll be able to understand this law. Make
Okay.
acceleration the object of formula and see what you have.
Okay.
So once you make acceleration subject of formula, you'll be having A equals to F over M. A equals to F over M. Now you can now see that truly the acceleration is directly proportional to the force, but inversely proportional to the mass, because the mass is under. So it's inversely proportional to the mass or directly proportional to the force. I don't know if it's clear now.
Yes, sir, it's clear, sir.
Okay, good. So let's proceed. So the law, the Newton's second law is very simple. If you can be able to remember this thing, it's always starting with acceleration, letter A. Is directly proportional to the F and inversely proportional to the M. Sorry, Ted? Sorry, please, you guys are not already saying something else. Please just try to turn off your mic so that to not distract other persons on the call. So if you want to speak up, you are free to turn on your mic, or if you are not speaking or if you're not talking, just try turning down your mic so that it would not distract other persons from hearing what I'm saying. So as I was saying, the formula is just something like AFM. You can't see my screen.
Okay, I can see
Can
it
you
now.
see it
Thank
now?
You.
Okay,
Yes, sir.
okay. So I said the formula is AFM. Just know that these parameters are the parameters that are inside the second law of Newton, the Newton's second law. A, F, and M. And A is directly proportional to F, but inversely proportional to M. So A is equal to F over M, which is the same thing as if you make F subject of formula, so it will be looking like the first law. That is making F the subject of formula. You now be having F is equal to MA. So that's why the Newton's second law is usually written as F equals to MA. That is, force is equal to the mass times the acceleration of that object. Force is always equal to, the applied force is always equal to the mass of that object times the acceleration that object is moving at. So this is the summary of the Newton's second law of motion. Is that simple? That's simple. So now this Newton's law, it explains how the same force will cause greater acceleration in a lighter object and smaller acceleration in a heavier one. So what this sentence is saying is, from this formula, we can see that if the force, assuming we had our force to be, say, 10, and our mass to be 2, assuming we had our force to be 10 and our mass to be 2, our acceleration would be 5. Because 2 times 5 is what will give us 10. Our acceleration will be 5. So, but now, assuming the mass is becoming bigger, the bigger the mass becomes, the smaller the acceleration for that particular force. So that meaning that if someone is getting fat, like someone is getting fat in size, and you push, let's say, let me think of one wrestler or one huge person. Okay, let me use a boxer, the popular boxer, Anthony Joshua, a popular Nigerian boxer. If he gives someone a punch, a slim person a punch, probably with a force of 10 Newton, gives a person a punch, the force of 10 Newton, a slim person's head would move with a faster acceleration compared to a fat person's head, because the fat person's head would move slower, would accelerate slower compared to the slim person's head, usually because of this law of motion. So the bigger the size of the object, the slower its acceleration for a particular force. And the smaller the size of an object, the higher the acceleration for a particular force. So if you hear what I'm saying a particular force, that is, if the force is constant, as the mass increases, the acceleration would also decrease. I don't know if I'm communicating at all. So when you use the same force, bigger objects would move slower, while smaller objects would move faster when you use the same force. So that's what this law tries to explain, and that's what this last sentence was trying to talk about. So now the key idea is that the more force you apply, the faster an object accelerates, unless the object is very massive. So now, objects would accelerate higher, but this acceleration can be affected by the mass. The higher the mass, the lower the acceleration. So that's just what this thing is saying. And it can be seen in the first law. Acceleration is inversely proportional to mass. So as mass is increasing, acceleration is decreasing. As mass is reducing, acceleration is increasing. So that's just the whole idea behind this Newton's second law of motion. So let's see whether we can move on to one of our examples. So now we have this basic example. We still have another example. This basic example said a 2 kg mass is accelerated at 3 meters per second square. Find the force. So now they already told us the mass of the object, and they tell us the acceleration, and they told us also the acceleration that the object is moving at. So now with this, let me use the same thing I used for the first law. When you start hearing about mass and acceleration, your mind should always be telling you first law, first law, first law, first law. Or when you hear force and acceleration, your mind should also be telling you first law, first law, first law. Because it's in this Newton's first law that when they are trying to compare mass and acceleration or force and acceleration, it's in the first law that you can see an expression that can work perfectly with this comparison. So when you see a question that I'm answering, yeah?
I can't see the screen, sir.
Okay, let me see.
I'm seeing
Can you
it
see it
now.
now?
Yes, sir.
Okay. Okay, thank you. Anytime you don't see my screen, just please call my attention so that I'll be able to do something from my end. So now, when you see this, when you see a question and you are seeing force and you're also seeing acceleration, your mind should ring second law. Professor, I said when you see coefficient of static friction and you are seeing force, once you're even seeing coefficient of static friction, your mind should always go straight to first law. So when you are seeing acceleration and you're now seeing force at the same time, or acceleration and mass, your mind should go to first law. And first law is that F is equal to mass and acceleration. So when you see a question that is that simple, where they're mentioning just these two parameters, your mind should go to second law, then look at if they're actually asking you for something relating to first or to second law rather. So now in this case, they said the mass of an object, they mentioned mass. Okay, we don't know where we're talking about. Is accelerated at mass and acceleration. That's second law. Your mind should always go to that direction. So what are they asking us to look for? Is usually supposed to be force. Then see it fully. They're asking you to find the force. So it's just simple. You just apply it. Mass and acceleration. That's 2 times 3. And you're getting your final answer as 6, your force. So this is the basic way that the equations under second law could come out as. So let's go to another example. How it would come out. So you can see my next slide. You can see the next slide I have here now. I don't know if you can see my slide.
Yeah,
Yes,
I can
sir.
see it.
Okay, can you see the new question that I have on my screen?
No, no, sir.
Yes, I can see.
I can see it now.
Okay, okay. So now this new question is, the question says the force of 2 Newton, they mentioned force, is applied to an object of mass 4 kg. Force and mass, second law. So I mentioned acceleration and mass, acceleration and force, but it could just know the parameters that are involved in this second law, force, mass, acceleration. So when you see 2 at the same time, either force and mass and acceleration, force and acceleration, just your mind should draw to second law. So now this question, they're asking us, the force of 20 Newton is applied to a 4 kilogram object. Calculate the acceleration. They've already told us the acceleration, what we are expecting. They now brought in another question. The distance, also calculate the distance moved in 5 seconds if it starts from rest. So if you were in our last class last week, sorry, don't mind me for where I'm using words, last class last week. If you were in our last class, that's kind of tautology. If you were in our last class, you'll be able to know that when you hear at rest, you should draw your mind to something, the equations of motion. When you start hearing at rest, your mind should start revolving around the equations of motion. That when they say something is at rest, initial velocity would always be equal to 0. When you start here and an object is at rest, U is equal to 0. I said it in our last class. If you're not in the last class, you could go to or soonest would be uploading the videos for the last physics class on the app once the app comes out this week. So you'll be seeing the video for all our previous night classes for all subjects when we launch the app this week. So for this, they asked us first for the acceleration, and we know that it's second law. So they're now asking us next for the distance moved in 5 seconds if it starts from rest. So now they've given us force and mass. So from these two, we can be able to get the acceleration, and we'll be able to get our question A. So now we have force, mass, and acceleration. So now they're now asking us for distance for our question B. They find the distance. So from the Newton's law of motion, the way I was trying to solve it that last time, I said, when you have that Newton's law of motion, you use all the formula, all the laws of motion. We have V is equal to U plus AT. That's one of the law. We have another one, V squared is equal to U squared plus 2AS. I said you should memorize all of them. And you have the next one, S is equal to UT plus 1 all over 2 AT. UC plus 1 all over 2 AT. So these are the Newton's law of motion. So the next thing you start looking for is which of them has all the parameters we have. We are looking for distance. That's what we are looking for in question B. So which of the formulas have distance? We know that this one and this one, they have distance. That's S. S is used to represent distance. So these two have distance. So now you will then look at the formulas. Which of them now looks like have the parameters we need? So now from the question, they said it starts from rest. Starting from rest means that they gave us U, our initial velocity as 0. So we can tick that this our formula has A. This our formula has A. That's A. Sorry, it has U. So we've seen that it has S. Now it has U. Then they also mentioned time. So this formula has time also. So already it's already telling us that this law of motion is out because this law of motion does not have time. So it's only this second one that has time and it has U. So most likely to have all we need. So and truly it has all we need. It has also A and it also has T. So they gave us U, they gave us T, they gave us A from our question. The initial velocity is 0 and the final velocity is, let me rub it off now. So I would not get distracted by it. So the initial velocity 0. So from this question now, we can see that the formula we're using is S is equal to UT plus half AT squared, where our U is equal to 0 because they said the object is at rest. Our A from question A, we've solved it and it's giving us 5. So now our T, they told us on question that in 5 seconds. So now we can put all these parameters in the formula and solve. And when we put it inside the formula, we'll be getting a final answer of 62.5. That's 2.5 meters as our distance. So that's exactly how the equation could come out again in your exams. To see it in this format, they could try to relate the laws of this second law. They could try to relate it with the laws of motion. So they could try to relate it to the law of motion. So they could do it the other way around, or don't worry, when we start solving past questions, or when we get to the past question types, we'll start seeing these kinds of things, how they are very simple. And now when you just understand it, you can solve almost any question, any calculation question, and you find that this is not really that difficult. So now this is how the questions come out. These are the types of questions that come out under the laws of motion, relationship with second law of motion in relationship with laws of motion. So now let's go to our next slide. So our next slide is question 2. So I hope you can see my screen now. I hope you guys can see my screen. Question 2.
Yes, sir.
Yes, sir, we
You
can.
can see it. Yes, sir.
Okay. So now let's move on. For Mr. Question 2, they said a 2 kg trolley. 2 kg, already telling us mass. Kg represents mass. So kilogram is always for mass. a 2 kg trolley is pulled up with a force of 10 Newton. We are seeing mass and force at the same time. Second law should ring. Across a smooth surface. Calculate. Second law now is playing out completely, the acceleration. So we know that it's acceleration. And now they say also calculate its velocity at 4 seconds. So now velocity, they're not mentioning velocity again. They're mentioning velocity again, taking us back to our general laws of motion. So let's see how we solve this. We'll use our second law, make A the subject of formula, as now be A equals F over M. And we put our F as 10 all over 2.5, which is our mass, and we'll be getting our acceleration to be 4. Getting our acceleration to be 4. So now going back to the laws of motion, we also have B is equal to U plus AT. I'm rewriting everything again. We also have V squared is equal to U squared plus 2AS. Then we also have S is equal to T plus 1 all over 2AT, AT squared. So these are the formulas for the equation of motion. The next thing we'll start checking, how many of the parameters do we have? We've already found our A.
Equation of is 4. They told us is 4, but you are giving us 3 here.
For which of them?
This one you're giving us, our teacher told us is 4.
Is it this equation of motion?
Yes.
Oh, okay, the fourth one is actually the formula for average velocity. And that one is average velocity. They would not, in most questions, they would not really mention average velocity. So sometimes they skip it as among the members of the major equations of motion, because you would barely see questions on average velocity. You barely. So the formula is just average velocity is equal to, and that average velocity does not link with this other three. These other three, you not see anywhere where they mention average velocity. So that one is just like a standalone formula most of the times, but it's among, just for your knowledge sake. So that formula is average velocity is equal to V plus U all over 2. Average velocity is equal to V plus U all over 2. So that one is not really that related to these three. They're the ones that are usually related to each other. So it's only in rare cases where they will give us questions that would involve average velocity. So that is the reason why most of the times you will see that some persons will talk about the laws of motion and they'll mention just these three. It's not really that they are actually three, but the last one is usually treated as negligible most of the times. So now looking at this now, we can see now that from our question, we have our A, we have our M. So we have our A acceleration. From our question, they also gave us that they gave us acceleration, they gave us time. And they're asking us for velocity. They gave us acceleration, they gave us time, and they're asking us for the velocity. So now they said a 2 kg trolley is pulled with a force of this across a surface. So now we would assume that the initial velocity before they started the pulling, the body was previously at rest, because for them to say they are pulling something means that before it was static. So you can assume that the initial velocity U is 0. I don't know whether you get. So you would assume that since the statement is saying is pulled, meaning that at the beginning, before this action happened, it was at rest before. So as it was at rest, now we can see that the initial velocity, since it's at rest, the initial velocity U will be equal to 0. So now we can say that they gave us U. So we'll look for the formulas that involve U. All three formulas involve U. So now they gave us T. Only two formulas involve T and U. This formula and this formula. It involves T and U. So now they are now asking us to look for velocity. This formula does not have velocity, but this one has velocity. So this formula is the only one that has all the parameters that we have in the equation. So we can use this formula straight up to solve. So such that to solve this, we'll then be using this first formula. This first formula that is V is equal to U plus AT. So using the formula that V is equal to U plus AT, we can see that that's what they did. We use our U as 0. Our A from the solving of question A as 4, and our time from the question as T being 4. When you add this into the formula or you compute it, you'll be having your final velocity to be 16 meters per second. So this will be the final velocity of the object. So this is how the questions can come out. They could merge the question and understand the main question, which would happen on a rare occasion. Most of the time, they would always want to merge second law with the equations of motion because it's one of the formula that is really related to those laws almost directly. So this is for your knowledge sake. So that's how the questions mostly come out when you see this topic. Or when you see questions like this is actually the way the questions are usually formulated. So you can go and try your past questions and see how many of those questions that you saw. I believe now it should be kind of clearer to you guys. So let's move on to the next slide. So on to this next slide now. We have the third law, the Newton's third law of motion. So Newton's third law states that for every action, there is an equal and opposite reaction. For every action, there is an equal and opposite reaction. So this Newton's law, it is that law that they've always been saying, for every action, there is an equal and opposite, there's an equal and opposite reaction. Most of the time, people just use it, even in English, to just say something. They just say it, for every action, there's an equal and opposite reaction. For every action, there's an equal and opposite reaction. Sometimes they don't really know that they're actually quoting one of the Newton's laws of motion, or one of the Newton's laws of motion. So that law of motion that they are quoting is actually this law, the third law of motion. Newton's third law of motion. So now, from what we have here, this law means that force always come in pair. That's when you are trying to push something, there's always a resistance that's always pushing back. When you're trying to push something, there's always a resistance that's always trying to push back. So this is what the law is trying to explain, that for every force rather, there is an equal and opposite reaction. So yeah, that's opposite. The statement is saying there's an equal and also there's an opposite. So meaning that if you are pushing forward, there is something that is actually pushing backward. If you're trying to pull something backward, there is something that is actually pulling it forward. So now let's see whether this thing is true. If you're trying to push a table forward, the frictional force trying to resist you from pushing the table forward, and frictional force will be acting towards you. So this frictional force is the force that is opposite to your pushing forward, your pushing force. So now that same table, if you're trying to pull it backward, friction will change its direction. Now it is always trying to oppose motion. I believe you should be able to see my screen now.
Yes, we can see.
Yes, we can see.
This is the third motion. So unlike most other laws of motion, this Newton's third law does not really have a formula per se. The formula is F is always equal to minus F. That's also whatever the forward force is, there's always an opposite reaction, always an opposite force that is equal and opposite. So if you see the statement of this law, the statement says for every action or for every force, you can replace it with that. There is an equal and opposite reaction. That is, there's an equal and opposite force. So the two things take away is it's equal and it's also opposite. So meaning that if you try to push a table forward, there is a force that is also pushing backwards. Is someone calling my attention to something?
Yes, you can see.
Can I see my screen?
Yes, you are seeing it now.
Okay, thank you. So for every force, there is always an equal and also opposite reaction. So now this, as I said, it means that every force always come in pair. If an object A, from what we have here, say if an object A of force, if an object A exerts a force on object B, then object B simultaneously is going to be exerting a force back. Someone is saying that they're not able to see my screen. Okay, I don't think your mic is locked. Everybody's mic is open. Everybody's mic is open, so I don't think anybody's mic is locked. But someone is saying, why is it like as though it's my mic that's not able to speak? I don't know. probably it's a setting from your phone or everybody is free to open their mic from our end. So now, I'm sorry about that, but you could use your what they call it, your chat in case you have a question. Someone is suggesting that you should rejoin the call. So probably you could try that too. Let's go on. Let's not get distracted. So this law explains various phenomena such as the recoil of a rocket propulsion in space or backward movement when someone jumps off it. So this is what it shows. This is what shows that what happens. This is what actually happens when you shoot a gun. The gun and you shoot the gun forward. There is something that the gun moves backward, moves the person that shoots the gun backward. So this is the law that is applied in that case. The key takeaway from this is that force always comes in equal and opposite pairs. No force exists in action. That's just the summary of this Newton's third law. There's not really a formula for that. Though there's a portion that is talking about momentum, but for this lesson, we're not really going into momentum yet. So let's head on to the next portion, friction. Friction. Does anyone have any question for the third law of motion?
No, sir.
Okay. So let's move on with friction. So friction, we probably have heard friction several times, even in relationship. You would also hear friction. In almost everything, you'll be hearing friction. Sometimes it even becomes like some persons might not even know that it's actually a physics related term. So friction is a resistive force that is said to act opposite to motion. So it is that force that the third law was talking about, that every time you're trying to move something forward, especially when they are moving an object that is in contact with another object. So now, before I try to say what I was trying to say, I need to draw out a line on friction. So for every force, there's always an equal and opposite force acting on that force, or be acting against that force. So this is true for all forces. But now, when you talk about friction specifically, it is talking for you to be sure that a particular opposing force is a frictional force. It has to be in between two objects that are in contact. It is the force that happens only in between two objects in contact. So if the object in motion is not in contact with anything, there is no business with friction in that case. It has to be in contact with another object. Like a balloon on the air. If you push it, you hit it upward. You are bouncing, hitting the balloon upward without it touching the floor. There is hardly friction. Or if you are using your mouth to blow breeze on the balloon, blowing the balloon up so that it should not fall to the ground, there is no business with friction and that motion. So the opposing force in that case now will be gravity, not friction. So when you talk about friction, it has to do with object in contact. It has to do with an object in contact. You have no business with friction if the bodies they are dealing with are not in contact with one another. So I have to spell this out so it would not just be like every force that opposes motion is called friction. So probably this will give some people a different idea when they try to talk about frictions and relationship. Probably they will know that, okay, if there is no fight, you can already say there's no clash between two parties. There is nothing like friction. It's not proper to say friction in a relationship or in any other stuff. For you to mention friction, it has to be relating to two things in contact with themselves before you be mentioning friction. So now, as an definition, I say it's resistive force that acts opposite to motion when two surfaces are in contact. So this is very important. So in case you are marking, sometimes if you've gotten admission into the university and you are trying to solve this question, or you're saying they might try to twist the options. They'll say it is the force acting opposing to an object. That is frictional force. The force that acts against an object. It is not always all force acts against an object in motion that's frictional force. It's only when they are in contact that you can mention friction. So emphasizing on this because it's very crucial that you understand that distinctive factor about friction. So now, it arises from microscopic irregularities between the surface. So friction would have not existed, or friction would not exist if the two surfaces in contact are completely smooth. No matter how we see that objects are smooth, no matter how it wants to be smooth, know how you want to smoothen a particular object, there will definitely be a form of roughness. A form of roughness. And so long as there's going to be a form of roughness, there will always be friction, but now the friction might be small. So friction will always arise as a result of irregularities. That's something that is not smooth. Irregularities between two surfaces in contact. So I just hope I'm making sense. So in ideal sense, they would say friction does not occur when when two surfaces in contact are smooth. But in real sense, there is no surface that's completely smooth. Every surface would have roughness, either in an eye view that you can see the roughness, or on a microscopic level where you cannot see the roughness. So there's always going to be roughness in almost every surface in real sense. There is difference between real and ideal. Ideal is something that is, you're just trying to emphasize or elaborate the sentence. But in real sense, there's no true smooth surface. So I'm just trying to establish it. So now factors that affect friction. Number one, the nature of the surface. So this is what I was trying to talk about, the nature of the surface. If a surface is smooth, the friction will be low. If a surface is rough, the friction will be high. If the surface is low, the friction will be, if the surface is smooth, the friction will be low. But if the surface is high, the friction will be, if the surface is rough, the friction will be high. So the friction, I said, is the opposing force. So now if you are trying to move a table on a rough ground, there will be a lot of hiccups trying to push it. But now if it's be on a smooth tile, it will just be, even if you don't really have much strength, just a small effort, you push it and to move because friction is low, because the surface is seeming smooth. So that's how the nature of the surface is one of the factors that affects friction. Another factor is the weight of the object or the normal force acting between the object. So at the beginning of this subject, I said something about normal force and weight. I said normal force is always equal to weight when the object is staying on the horizontal surface. So now, normal force, whether it is the normal force that is equal to weight or the one that is not equal to weight, it can affect friction. Also, weight can also affect friction. So these are the factors that can affect friction. So if an object is very heavy, it will be difficult to move it, and that its weight would add more energy to the friction. So it would oppose the motion more because every force that's opposing motion, they sum up to become friction. So the weight is also a factor that determines friction. Another factor that determines it is surface area. Surface area, how large the surface is, how small the surface is. This stuff, if the surface is very wide, if the surface area of the object is very wide, if it's very large, if the surface area is very large, the friction will be less. If the surface area is very small, the friction will be high. If the surface area is very light, the friction will be low. If the surface area is very big, the friction will be high. So this I know that I'm not sure you might be able to understand this very well, but this is the reason why powder is kind of a lubricant, because the surface area of powdered materials, of powder, is very large. The surface area is very large in powder, while things that are just huge solid, like if you take a ball of chalk and you want to rub it over a surface, a ball of chalk, like a stroke of chalk, you want to move it on the board, there is a lot of opposition. But ground that same ball of chalk, ground it to powder, that is to make it have more surface area, ground it to powder, and rub it across that same surface. You see how smooth it will move. So this is how surface area affects friction. So when the surface area is large, it's something that you need to write down, but I think it's people that are more, some persons might really catch what I mean by surface area large. So when you talk about surface area being large, it means that the particle is tiny. The tinier the particle, the larger the surface area. The bigger the particle, the smaller the surface area. I think this would help to relate. So if you're writing, just before you write, after you write surface area, just write it somewhere. The tiny the particle, the larger the surface area. The larger the particle, the tinier the surface area. So now, large surface area improves Large surface area means that there is low friction. That is tiny means there is low friction. Tiny surfaces, tiny particles means low friction, but larger particles means high friction. I don't know if someone can get what I'm saying, Sha, but let me just explain the last one so I can throw out the question if you don't understand. So I could explain it better. So the final one is presence of lubricants or contaminants. So lubricants are materials that we know, like oil. These things, they tend to smoothen the surface of a particular material. They tend to increase the surface texture of something, lubricant. So when you apply lubricant, it tends to make an object surface more smooth, and this would affect friction, as we know that smoothness affects friction. So does anybody have any question before I move on to the next slide? Does anybody have any question before I move on to the next slide? Okay, I would assume that everyone understands what I'm saying. So let's assume that everyone understands what I'm saying. So let's move on to the next slide. This next slide talking about uses of friction. So I'll just be rushing through this because our time, we're running out of time. Use of friction. We have friction enables walking without slipping. So as mean there was no friction, as mean the ground is very smooth. People will fall. People will fall very well. It allows vehicles to grip roads well. That's the reason why they make the surface of what they call it of your tire rough. Because when it is rough, friction is more. So if it is not rough, if the tire is so smooth, accidents will be plenty because the materials, the cars will be moving carelessly because they'll be sliding away. They will easily slide and it will be misleading to the driver. And for accidents would happen. So friction, it allows the good thing about friction is that it allows us to be able to walk well. And I think that's the reason why God made under our feet. He made under our feet not just smooth, he made it rough. So that's the reason why God made it like that. Made our feet have rough texture so we can be able to walk well because it's rough. We will not fall regularly. If you see small children, babies, their legs are smooth and somehow they find it difficult to walk. If they try to walk, sometimes they can easily fall because their leg is, the friction there is low. But let's leave that. Let me just not go down into that because it will just spend more time. We have less time and we still have a lot. So it enables brakes to stop motion. It also helps in writing with pencils and pen, and it also provides grips in machines and tools. So these uses, I think it's best that we know this, at least these 5. Know them offhand. Just know them offhand. These 5, know them offhand because sometimes you might be given theory questions saying, what are the state uses of friction? And before you know, you'll be surprised that you just don't know them or you've forgotten the uses. So these uses are the same as the advantages of friction. So you could see them as uses of friction or advantages of friction. So these are the uses and advantages of friction. So the disadvantages of friction are it causes wear and tear. So when surfaces are rough and trying to rub them across each other, it will cause them to start peeling. They will start peeling on themselves as they are rough between themselves. So that's what they mean by it. It causes wear and tear. It also reduces efficiency of machine. Once the friction is high, it will make a machine consume more energy to perform itself because it's trying to, it will first have to overcome friction for it to move, especially in machines that move. They would have to overcome a lot of energy. You have to overcome friction, which is high when the surfaces are rough. You have to overcome friction first, and that is consuming energy before they can be able to do the real task you're trying to do. So it's not really good for machine efficiency. It produces unwanted heat. When you rub your palm across itself to generate heat, if it's a machine, just think of what will happen. As the machines are moving with higher speed, it will generate more heat. And this heat can be unwanted in some cases, except you really need it. So then the fourth disadvantage is that it increases the energy consumption in machinery. This is related to the second law. It's similar to the second law. It causes it reduces the efficiency and also ends up increasing the energy consumptions machines. So let's go to the next slide. Types of friction. I hope everyone can see my screen. Types of friction. I hope everyone
Yes,
Yes,
can see
sir.
my screen. Okay. So let's go to types of
Yes,
friction
sir.
now. There are like 5 types of friction. I think 5 types of friction, and it's important that we know these 5 types. So here I try to summarize the definition of friction and okay, it's four types of friction. So these four types of friction, we have static friction. So this is the friction this is frictional force that prevents a stationary object from moving when force is applied. So as the name implies, static, it is the kind of friction that resists an object when it is not yet moving. It tries to prevent an object to start moving. It prevents an object from starting to move. It is called a static friction, and it's related to somehow it's kind of that friction that is related to the first law of Newton's, the first Newton's law. Questions of static friction, if you can remember. So this frictional force is the one that is related to that one. So it is the force that is the frictional force that exists when an object is not moving. Example, when you have a box standing on a surface without moving, the force that is resisting it from moving is static friction. So the next slide. So they said the key point for static friction is that it increases with applied force. As force applied increases. So it increases with applied force until it reaches the maximum limit beyond which the object starts moving. So in this sense, it is relating to the third law. We said for every force, there's an equal and opposite reaction. So if you put small force, let's assume we had a rock, we are trying to push the rock, big rock, we are using small energy or small force to push that rock. The frictional force will be equal to our force. And so let's assume we are pushing with 10 newtons. The frictional force should be exactly 10 newtons. If we increase our force to 20 newtons, the frictional force will also increase to 20 newtons. So the only time that this static friction we can overcome, this object can move, is when we can overcome this static friction. So I think the energy required to move this object is 50 newtons. If we push it at 40, the frictional force would also be 40. As the force is increasing, the applied force is increasing, so is the frictional force increasing until you can overcome this frictional force, until it reaches its maximum value and you overcome it. That's when the object will start moving. So that is what this key point take away from this sentence. Static friction increases as applied force increases, except these static frictions, the maximum static friction is being overcome, then the object will start moving. So these are key points that you should just take note of in static friction, because they could come out in objective questions, any form, any shape. So they can come out like that. Let's go on to the next slide. Limiting friction. The second type of friction, limiting friction. So this is the maximum value of static friction just before the object begins to move. So now we are talking about static friction, and we said static friction is it continuously increases. So static friction is the force that is opposing a motion when an object is not moving. So it continuously increases as you apply more force. So the maximum static friction is the same thing as the limiting friction. If you want to write, you can write it down. The maximum static friction is equal to the limiting friction. So this limiting friction is the maximum value of the static friction. So it is that frictional force that is the last frictional force, like the last energy of friction to oppose any motion, that once you overcome this limiting friction, the object will start moving. So that is another type of friction. It's called the limiting friction. So the example is not really something that is visual or you can understand very well. It's not something that we can really visualize. I mean, not that you cannot understand, but you might not be able to visualize it very well. But it's just that last energy that friction has to exert on anybody that is trying to move an object. Once you overcome that friction, that last energy is called the limiting friction. So now, once it's overcome, the object will begin to move. So the third type of friction is called kinetic friction or dynamic friction. Kinetic friction or dynamic friction. So this is the kind of friction that occurs on objects that are already in motion. So when your hand is gliding across itself, you are rubbing your palms across itself. There is also friction, but that kind of friction that is there is not static friction. It's called dynamic friction because the friction is still there. The opposition to the motion is still there. But now it is not a static opposition, it is a dynamic opposition. So this kind of friction is called dynamic friction. It's always opposite in direction of movement. So now, it is the kind of friction that is seen in sliding and rolling of objects. So these are the types of static friction that's seen is it's kinetic friction or dynamic friction that's seen in moving objects, like rolling objects or sliding objects. When you slide your palm across themselves or across a surface, the dynamic friction you're experiencing. So the key point is that this kinetic friction, it resists ongoing motion, but is generally weaker than the static friction. So its own resistance is less because it is there, but feel like say they. Pardon my pidgin, but we are Nigerians. It is there, but it's like as if it's not there. Because the applied force is always greater than it. Dynamic friction, the applied force is always greater than dynamic friction. Dynamic friction, the applied force is always greater than the dynamic friction. So it's important that you should write this thing down because it comes out in your question, exam question that say, what type of friction? In what type of friction? Or they could just twist it anyway and say, the friction that exists when an object is moving or is in motion is called dash. And they would mention all sorts of nonsense. And you might not know why the answer is just dynamic friction or kinetic friction. So that's important that you take note of that. So as you're writing, you could write that down. So let's go on to the fourth type of friction. And this fourth type is called fluid friction. Fluid friction. So this fluid friction is the kind of friction that is seen in liquids. It's also known as viscous drag, and it's kind of related to the viscosity of a particular liquid. So it is the liquid, let me not just say it from my head because we have it, so I will not just say something. So this is the resistance experienced by an object moving through a fluid. So now, when you drop, probably, we have oil. When you drop something inside oil, maybe a plastic cover inside oil, or a plastic material that has weight small inside oil, it will move down inside the oil slowly. Or if you drop some objects inside some kind of fluid, drop them inside the object, inside the fluid, they would move slowly compared to lighter liquids. Maybe water, comparing water and oil. If you drop some materials inside water, it will drop faster. There is less friction because of water is less viscous. So when you drop that same material inside oil, because oil is more viscous, the frictional force is more. So now it's important that you should write that in viscous liquid, just write this one on your notes. In viscous liquid, fluid friction is always higher. The higher the viscosity, the higher the fluid friction. So I'm just trying to use two ways to say it. In viscous liquid, the fluid friction is always high. In other words, you can say that the higher the viscosity, the higher the fluid friction. So the thicker the solution, the thicker the fluid. That's just what I mean. So that's for fluid friction, and it's also known as viscous drag. So now the quick recap on everything I've been saying so far is static friction occurs before motion when an object is at rest. Limiting friction occurs before motion begins. Occurs before motion begins is that last point, the dying minute of static friction is limiting friction. And it can be said it occurs at the threshold of motion. Then we have kinetic friction. It occurs during motion. Sliding or rolling motion. It occurs during motion. So they mention sliding and rolling because the object has to be in contact with themselves. For you to mention that they are friction is a frictional force, that's being in contact. So the way things are in contact, when things are in contact, they either roll across each other or they slide across each other. So it's always the type of friction that occurs in motion. Then fluid friction also occurs when the object is in motion, but in a fluid. So that's actually the types. These are the types of frictions. So let's go to the next slide. Equilibrium of forces. Equilibrium of forces. So that a body is said to be at equilibrium rather, when the net force is equal to 0. A body is said to be at equilibrium when net force is equal to 0. Our time is up, but let me see how much I can just chip in. before time goes a little bit. So at least between now and 10:15, I will see whether we could round up. We have like 12 minutes, so let's just hurry up. So when you talk about equilibrium of forces, it is when equilibrium of forces occurs when the force is acting on a body, when the total force acting on a body is equal to 0. That's both the upward force is equal to the downward force, the left force is equal to the right force, the side force is equal to the opposite right side force. So when you add all these forces and it gives you 0, you can say that there is equilibrium of forces. When the net of all the forces acting on a body is equal to 0, you can say that there's equilibrium of force. So let me bring this thing down to a realistic or to a pictographic view. You are trying to push an object forward, and also the object is trying to push you backwards. So this is what actually happens every time. So when these objects will remain at equilibrium, it will remain in the same way if the force pushing it forward is always equal to the force pushing it backward. So that's the total force is forward force plus backward force, and backward force is always in negative. So F plus minus F, giving us 0. When you add this thing and the thing is giving you 0, when the total force acting on a body is equal to 0, you can say that the object is at equilibrium. That's equilibrium. So now, we say that there are two types of equilibrium: static equilibrium and there is dynamic equilibrium. So static equilibrium is what happens when the object is at rest. When the object is at rest. So while dynamic equilibrium is one that occurs when an object is in motion rather. So when an object is in motion, it is said to be in dynamic equilibrium. So this type of dynamic equilibrium is something that happens when you see something like all this our seesaw, or jangloba when we are small. That's one person will sit at one end, the other person will sit at the other end, and both people they have the same weight and they keep on bouncing at the same force. When they keep on bouncing at the same force, when the both of them have equal force, when both of them have equal force downward, like their downward force is always equal to the upward force. When both of them's forces are equal, the object will remain in equilibrium, static. But now, if they are pushing the same force downward and upward, the object will continuously moving downward and upward continuously. And this, when they are moving continuously and they are not stopping at the same speed, the same sync, the same movement pattern, it's said to be in dynamic equilibrium. It is moving, but it is moving at the same force, the same distance. It's not going higher than the first one. The movements are always equal measurement. Dynamic equilibrium. It's called dynamic equilibrium. So let's go on to the next slide so we'll not waste much time. So the conditions for dynamic equilibrium. Condition for dynamic equilibrium is that the sum of all the horizontal forces must be equal to 0. And the sum of all the vertical forces must be equal to 0. Also, the sum of all the moments of all force must be equal to 0. Must be equal to 0. The moment of all forces must be equal to 0. For some reasons, I did not really give image to explain this thing. Or is the seesaw example I was trying to give you, and is that kind of experience? Is this stuff that they talk about when we try to balance a meter rule on knife edge? There's sometimes that you balance it and you just touch one tip, the meter rule will just be dangling, keep on dangling, but it will not fall. It just keep on dangling. At that state, it is at dynamic equilibrium. It is not taking an extra movement. It's just maintaining the same rhythm of movement. So at that state, it's a dynamic. It's moving, but it is moving at equal intervals. So that's what dynamic. So before equilibrium can happen, the upward force must be equal to the downward force. The horizontal forces, all the horizontal forces must be equal. Also, the movements of all forces must also be equal. That's the sum of all of them must be equal to 0. So let's move on to the next slide. Lami's theory. So I'd really love to give to solve more on this, but for this thing, for the sake of this class, I would not be solving, but I'll be explaining this thing very clearly. So when we talk about Lami's theorem, it's a theorem that's under dynamics. It's one of the theorems that are when you talk about dynamics, they are involved. It's called Lami's theorem, and it's actually a theorem that happens in three coplanar forces. When you have three forces on the same plane acting on a single object. 3 forces on the same plane acting on the same object. So they are called coplanar forces. They are called coplanar forces. Forces that are on the same plane and acting on the same object. They are called coplanar forces. So then they said this theorem is used when you have 3 coplanar forces that are in equilibrium acting on a particular object at a point. So now this theorem said that if a body is in equilibrium under the action of 3 coplanar forces and the concurrent forces, under the action of 3 coplanar and concurrent forces, each force is proportional to the sine of the angle between other two. So all the grammar is just, let me use my illustrator now. So now we have this thing here. So the force of this one, the sine of the angle of this one, of one side, and the force is always equal to sine of the angle of another side. This formula here, you can see here, F over sine for the angle behind sine is always equal to F. That is, so long as they are at equilibrium, the F of this one times the F of this one over the angle here is equal to the F of this one over the angle here, equals to the F of the angle of this one, the F of this one over the angle here. So just look at a force, the angle that is immediately behind it is what they are using. The force over the angle that is immediately behind it, and that force over the angle that is immediately behind it is equal to another force over the angle that is immediately behind it. So that's how this formula, that's how you can memorize this formula. When you have y, one of the leg of the y is equal to the angle, the force on one leg of the y is equal to the angle on the other two. As at the back of that one. I don't know whether you are understanding, but the force here is equal to the angle over the angle. Sorry, not equal to. The force over the angle above it is equal to the force on the other side over the angle behind it is equal to the force on the next side over the angle behind them. So that's just how the formula happens. Such that you can now have F1 over alpha over sine of alpha. Sorry, sine of all these angles. I was omitting sine or sine of it. So F1 over sine alpha is equal to F2 over sine beta is equal to F3 over sine gamma. So the main thing is not whether it's F1 or F2 or F3. You can see in some places where they will say A, B, C. So now, what they're just trying to tell you is that whatsoever force you are picking, the angle that is behind it is what is always under it in the formula. And it's always equal to another force over the angle behind it. That is the sine of the angle behind it. So that's the simplified form or the way that you don't need to cram this Lamis theorem. You could see solvings on it. So the question, solving that usually come on it is, they will give you one of the force and give you one of the angle or two of the angles and tell you to find the other force. Or they could give you two of the force or two of the forces, give you one angle, tell you to find the other angle. So this is actually the way the questions come out. Either they'll give you two force and one angle, or they'll give you two angles and one force. And it's just for you to combine them together and solve to get your final answer. So I don't really have time and I didn't even put an example yet. But that's actually the simplified form of this solving. So where this F in this formula represents force, and these alpha, beta, and gamma, they represent angles. So now let's head on to say the key idea. Said when three forces keep a body still, their relationship follows Lamis theorem through angles and sine functions. So this is just part of the English that I just said so far. Part of the English I've been speaking so far. So this is the formula for Lamis theorem. In case you see it in the option, I give you, click it somehow. Maybe they'll give you, say which of this formula is Lamis theorem, or which formula or which theorem is applied three coplanar forces at equilibrium. That's one way you see it. Which theorem is applied in three coplanar forces at equilibrium? Or they could tell you to state Lamis theorem. So either ways, these are the ways that questions can come out from this. So it's best you would know the Lamis theorem and know where it is applied. and also know the formula. It's actually very simple. We don't really mention much formulas since the beginning of this course. You can memorize all the formulas we mentioned since today. You are good to go. Let's see how far. So inclined plane, I think I would have to, let me see, sorry, I think I would have to, I think I'll have to stop at this inclined plane because that's actually the end of this lesson. Let me see, that's the end before we reach conclusion. So let me just see how we can just touch on these inclined planes. So at the beginning, I was saying something about inclined planes, that an object can be on horizontal. And I mentioned slightly, I said it could also be on an inclined plane. An inclined plane is something like this. Let me use my pencil. So it's something like this. Something like this, where you have a plane that is at an angle. So the plane we're talking about is, let me change the color for this plane, is this red place, this red portion. So this is the inclined plane. It's inclined at an angle, this angle here. So every inclined plane is always inclined at an angle. So the inclined, for an inclined plane, there is the way that you treat the forces that are acting on these inclined planes. It's actually a way that you treat the forces that act on this inclined plane. So the forces could be either parallel to the inclined plane. That is, you can see a force like this. Let's assume this is the object. The force, when it's parallel, it means that the force is acting in similar direction to the inclined plane, either slanting downward or slanting upward. So when the force is acting on this in parallel to the inclined plane, the formula for it would use sine theta. When it's in parallel, you use mg sine theta. Force is going to be equal to mg sine theta when the force on an inclined plane is acting parallel to that inclined plane. The formula, that force will be equal to the mass of the object times gravity sine angle of the inclined plane. The mass of the object times gravity times sine of the angle of the inclined plane. So let's go back to this. So now this force, this kind of force now, they're acting parallel to the inclined plane. To get them, you use mg sine theta. Use mg sine theta. That's the mass of this object times acceleration due to gravity times the sine of the angle of this inclined plane, this angle down here. So now, when it is now, the force is now perpendicular to the inclined plane. What I mean by perpendicular means this is the inclined plane. But now the force is acting at 90 degrees to the inclined plane. Acting at 90 degrees to the inclined plane. So at this case now, the force now that is acting at 90 degrees, either upwards or in this direction, is going to be mg cos theta. Sorry. Oh, sorry. Let me stop my device before it goes up. Sorry about that. I just saw my battery is low. Okay. So now, this is for the force that's acting horizontal to this inclined plane. This is how the laws are. This is how they resolve forces on the inclined plane. They are usually having this formula. When you're asking to look for a force, the force they're asking you to look for is perpendicular to the inclined plane. That force is equal to mg cos theta. But if the force that they're asking you to look for parallel to the inclined plane, that force is going to be equal to mg sine theta. So that's for that one. That's what this place is saying. That's what I have on the side. It's equal to mg sine theta when it's perpendicular to the inclined plane. It's going to be mg cos theta. When it's parallel, it's mg sine theta. Such that the question they could ask you, an object on an inclined plane has a mass of 10 kg. If the inclined plane is inclined at an angle of 30 degrees, what is the force? What is the frictional force? Because frictional force will be acting parallel to the plane. So what is the frictional force? They could see a question like that. So it's just say F is equal to mg sine theta. We know our G is 9.8. That is acceleration due to gravity, or 10. Our mass, they're giving us from question that mass is equal to 10. And the angle of the inclined plane, they've given us 30. So you just solve it to your calculator and you get your answer for frictional force. Because they mentioned that the frictional force and frictional force. So let me even mention this thing. Take notes. Frictional force, take notes. Frictional force on an inclined plane is always parallel. Frictional force on an inclined plane is always parallel to the inclined plane. So it's always parallel to the inclined plane. Frictional force on an inclined plane, on an object, on an inclined plane is always parallel to the inclined plane. So whenever they ask you for frictional force and they're relating it to inclined plane, just know that you would equate the mg cos theta, because mg sine theta, because the frictional force is always parallel to the inclined plane. So however, if they're asking you for the normal is always perpendicular. So the normal force is always perpendicular to the inclined plane. The normal force is always perpendicular to the inclined plane, because normal force is always perpendicular to the plane that an object is standing upon. The normal force is always perpendicular to the inclined plane. So that is the formulas for forces acting on an inclined plane. So now let's see how examples come out in this inclined plane. So this is an example now. They're asking us to.
Hello, sir. Hello,
Yeah.
sir.
Yeah.
Please, I don't, from the diagram you showed, I didn't understand the perpendicular, how the thing is perpendicular to the inclined plane.
Okay.
You said that
So
the angle
let's
has to be 90 degrees.
let me erase everything and show it clearly again. Now let's play again. So now we have this. This is an inclined plane. This is a horizontal plane. Then we have an inclined plane now on this angle. So there's an angle here. So perpendicular to the inclined plane means that it is at 90 degrees to the inclined plane. That is something like this. Like this. Like this. It's at 90 degrees. This is the plane. So 90 degrees is like this. The force that is acting like this is perpendicular to it. And whenever the force that they're asking you to find, like the normal, forces that are usually perpendicular to the inclined plane are the normal. Normal is usually perpendicular to the inclined plane. Normal is usually perpendicular to the inclined plane, while friction is usually parallel to the inclined plane. So frictional force, if an object was standing on top of this inclined plane, the object will want to go down, will want to slide down. If an object was on top of this thing, the object will want to slide down, So this sliding down this plane is a movement that is parallel to this plane. The plane is moving, is like this, it's slanted. The force also is still slanted, same direction with the plane. But that force is going to be parallel. So now, because of that, as I said, frictional force are always parallel to the inclined plane. Frictional forces are always parallel to the inclined plane. I don't know whether it's clear now. So normal force is always perpendicular to the inclined plane. And because of that, we'll use the perpendicular formula. While frictional force is always parallel, normal force is always perpendicular. Frictional force is always parallel to the inclined plane. So then we'll then use the formulas for perpendicularity and for parallel cases. I don't know whether it's clear now.
Show the formula again for perpendicular.
This is the formula again. This is the formula here.
Okay, mg cos theta.
Yes, mg cos theta is for perpendicular. Mg sin theta is for parallel. So for the sake of time, we'll be stopping at this example, because I think after the example, we have just experiment. An experiment is just an explanation of something that I've explained before. So after the experiment, we just have conclusion, and that's all. That's all. So after this example, I think I'll be stopping after this example. So this example now, we have that a 5 kg mass, a 5 kg body on a 30 degrees incline, that is an inclined plane. Find the force down the incline. That is the force that is going as for the object to move down the inclined plane. Find the force for the object to move down the inclined plane. So the force for the object to move down the inclined plane is going to be parallel to the inclined plane. It's going to be parallel because for the object to move down the inclined plane, it has to be moving in the same, the force has to be in the same direction with the inclined plane. Let me say what I mean here. Let me draw it here. So we have inclined plane here. We have an angle here, 30 degrees. And we have an angle here, 30 degrees. An angle here, 30 degrees. Then we have an object on top of this inclined plane. An object. So for this object to move, it has to go down like this. For this object to move down the inclined plane, it has to go down. So if you look at the direction of this force, is parallel to the same direction of this inclined plane. So because it's parallel, we already know now that it is the formula for parallel movement that we're going to use. So now they're not asking us to find out force to move down the plane. So the force is F equals to mg sine theta. So mg sine theta now, we know our theta as 30. We know our gravity, our attention to gravity as 9 points, and they gave us the mass as 5. So if you do the mass, you'll be getting your final answer to be 24.5. Getting your final answer to be 24.5. So that is just how we solve questions under inclined plane. They are usually in this pattern. Here they would ask you that the force acting downwards. They might give you the force acting downward, and they'll tell you to find the angle. They might give you the force acting downward and tell you to find the angle of the inclined plane. They might tell you that the force acting downward is this, and there is a and they define the angle, find the angle. They could tell you to find the angle. They could give you the angle, give you the force, and tell you to find the mass. So you just get out the way. It's just normal mass. Just find your way to think about it and get the final answer. So with that being said, any question? So I would know if we end the class.
What if the force is acting upwards?
If the force is acting upward, it's still going to be the same formula. Because the upwards is also, see it here, upwards is also parallel to. Do you get it? You know that this force that is moving downward now is the normal force that they're asking us for. So from the third law, I said for every force, there's an equal and opposite force. So even for this downward force, there's also an upward force. And that upward force is also parallel to this thing. And that upward force must be equal. Because from third law, it's equal and opposite. So it has to be equal to this same thing. So it will now be negative. That's opposite. That force that is moving downward. So now if we found the force to move it down to be 24.5, the frictional force, which is the opposing force acting upward, would then be minus 24.5, because for every force, there is an equal and opposite force acting on an object. For every forward force, there's an equal backward force. I don't know whether it's clear. So since it is equal,
which one will be minus? Is it when it's acting upwards?
If the applied force is upwards, the downward force will be minus. If the applied force is downwards, the negative force will be backwards. So it depends on where the applied force is coming from. If the applied force is coming from down, the force that is opposing it, which is the frictional force, will be minus upward. So if the force applied is upwards, pulling it upwards, the frictional force against it will be downward and to be minus. I don't know whether it's clear like that. So the minus is not actually meaning that the value is negative. It just means that it's trying to indicate that it's opposite to the applied force. I hope it's clear now.
It's not clear. I'm confused.
So why
Let me try.
0.8?
Yeah,
I think so. Yes, I said why is our G 9.8?
I think you should.
Okay, G is 9.8 because that's like the approximate value. They mostly round it up to 10 most of the times. But the real value by experiment, the experimental value of the acceleration due to gravity is 9.8 something practically. So most of the times they always want to prefer to leave it as 9 point, while in some cases they can make it 10. I don't know whether that question I've answered your question.
Thank you, sir.
Okay, so now
Sir,
back to the
I got
explanation that I was trying to.
24.5.
Yeah, that's the answer. 24.5 is the answer.
Okay, sir. Thank you.
Yeah, thank you. So now back to this example I was trying to explain. I said when the force, the applied force, there are always two forces. The person that I was saying that she was confused about applied force, there are always two forces, applied force and frictional force. So if you are applying force upward, friction will be backward. If you are applying force downward, friction will be upwards. So now, whatever the applied force is, friction would always be opposite of it. That is always have a negative sign. So that's just what I'm saying. So if the applied force is pulling the object downwards, the frictional force that is the opposite force to it be minus the applied force. If the applied force is upward, the friction that is opposite it, that is backward, then minus the applied. So that is just the way it is. If the applied force is moving downwards, the frictional force will be moving upward. If the applied force is moving upward, the frictional force will be moving downwards. So that's just the whole thing I was trying to say so far. And this frictional force will always be equal to the applied force. Always. It's usually always equal to the applied force at every time. It's always increasing with the applied force. Remember I mentioned it. So for some reasons, my class will be ending here. And I'll be saying good night, everyone.